Hi everyone, and welcome to another
The Earth is flat on planet Pluto.
an online live cosmic talk show about astronomy, science, and other stuff where the guests are the clear highlight and where you can ask any questions and also participate by using the chat here. And the voice from beyond, which you can meet today, finally will collect the questions and I'll provide them to our guests, which will enlighten us with a lot of knowledge. Now, every Wednesday at 5:30 p.m., we'll try to bring you a cosmic topic and amazing guests who will share their passion for science and space. In this third episode, just like all the others, things can and will definitely go wrong. I mean, the sound will probably break, the video might have failed. And I must stress that this is obviously part of the program because it's part of the scientific method. We need to blow things up. I mean, this is how we've learned about the structure of matter, and hopefully this is how we'll continue to discover new things in the subatomic world. And also because when things work perfectly, we never really learn anything at all. During June and July, I shall be your host as we attempt to bring you lots of astronomy, science experiences, the human side of looking up, and also a lot of fully random but hopefully fun stuff. My name is David Sobral, and I'm an astronomer and a scientist. And just like everyone else on this amazing yet insignificant planet, I'm 90% made of stars and 10% made of cosmos. Yet, all that, I mean, stars, gas, dust, atoms, molecules, you have it. That's just 5% of all there is in the universe. So if you didn't know, we are the 5%, and we know so little about 95% of all that's out there. So that might be spooky, challenging, and overwhelming, but it seems to be the truth. Now, today's guests are fascinated with this invisible and mysterious side of the universe, and I would say so should you, because there is still so much to discover about what we call dark matter and dark energy. Today, you can also ask all the questions you always wanted to ask about the invisible universe, again, just using the chat. So without further ado, please welcome Karolina Wresilo and John Carrick. Our audience is really enthusiastic to get to know more about what we can't see. So thank you a lot for coming into the show, and thank you, Karolina, for coming back. I hope you enjoyed last time, and we'll cover much more today. And I'll probably start with you. So it seems like the things that make us are just 5%. So what the hell is the 95%? Do we even know?
So obviously at the moment, from cosmological observations, we think that around 25% of all of the content of the universe is this so-called dark matter, whereas the ordinary matter that we see all around us, as David has mentioned, constitutes only 5% of everything we observe. And that would mean that around 70% of everything else is made up by the dark energy, which we believe is responsible for the accelerated expansion of the universe. However, still, to this day, we are quite not sure what the hell dark energy and dark matter are.
So talking first about dark matter, how do we know that it exists? I mean, if we can't see something, how can you believe in it?
Yeah, so there are actually numerous pieces of evidence for dark matter today. I think the most important one, and one of the earliest pieces of evidence, is the rotation, the velocity plots of galaxy rotation curves. So basically, when we plot the rotational velocity of a galaxy as a function of distance from the center, based on what we see, based on the matter we observe, we expect this velocity to decrease as we move away from the center. However, when we do actually observe this, we find that this velocity stays approximately constant. Due to this, we think that there must be some kind of extra type of matter present, away from the center of the galaxy, which would make it rotate faster than we expected, Other than that, there are things like galaxy mergers. So, for example, when we observe galaxies merging, and when we look at the dynamics of the whole phenomenon, we see that what we expect from theory doesn't agree with what we're observing, and that can only be explained if, again, there is this kind of invisible matter surrounding them.
And I mean, those observations of rotation curves or galaxies spinning as too fast without having extra matter, I mean, those are pretty important observations. So I'm sure it got like at least one Nobel Prize, right?
Yeah, you'd hope so.
So who did it? I mean, is it a famous person? Do people know about her?
Well, I would believe that she is famous. Her name is Vera Rubin. She's actually the person that did discover that galaxies are rotating faster than what we would be expecting. Unfortunately, during the time in which Vera Rubin worked, astronomy was largely dominated by men, which I do expect that it made it a lot harder for her to work. I bet she must have faced a lot of sexism from her colleagues. She must have been discouraged from doing research. Yet she broke those stereotypes, and she was one of the most important people in astronomy, arguably, and she was also a female.
So I guess for people watching us at home, and they're really loud, you can always hear them. It'd be really cool to put on the chat those that actually have heard about Vera Rubin, because it's really quite outstanding that someone that did something so fundamental and important is not as well known. Although maybe, as John will tell us all, she finally got a telescope named after her. So I think we're on the right track. Now, John, so you're doing a PhD that is very much related with this other component of the universe, which is dark energy. So
that's right.
How the hell did we discover dark energy? Was it also Vera Rubin? Was it someone else?
So it wasn't Vera Rubin in this case. There were two separate independent studies in the late 90s that were looking at distant supernovae. And these were used to parameterize the universe's expansion. So they used specifically type 1a supernovae because these are known as standard candles. That means they explode at the same mass and therefore the same brightness. So when we see them from Earth, how bright they appear in the sky will tell us how far away they are. So when you've got many of these supernovae, you can essentially see the expansion history of the universe. And as previously mentioned, this was evidence that the expansion is actually accelerating. So to explain this, the cosmological models that we use require some additional energy that is separate from matter. So this is the evidence for dark energy.
And how much dark energy then is it out there? Just how much?
So how much? I mean, it's a good question. Like in terms of the total energy of the universe, it's about 70%, which seems pretty crazy, really, because dark energy is essentially the energy associated with just empty space, just vacuum. So it's pretty overwhelming to think of the energy of nothingness greatly exceeding that of, huge things like galaxies. But as we don't know the true nature of dark energy, it's hard to know, what extent it really has on the universe.
So, for example, are we absolutely sure that dark energy is like it exists for sure, or could our models just have it wrong?
Well, the whole idea of dark energy hinges on the fact that we're assuming general relativity is correct. So I'd be inclined to believe that this is the case. I mean, there's so much evidence already that general relativity is correct. For example, you can look at light bending around the sun during an eclipse, or the orbit of Mercury. They all follow exactly what's predicted by general relativity. And it's even proved today, like a few years ago, gravitational waves were directly observed, a prediction of general relativity over 100 years ago. So either general relativity is correct and this dark energy exists, or there's something fundamentally we don't understand about gravity. So we'd have to rethink the whole physics behind it to explain dark energy then.
So the other thing is, so you're doing a PhD with Professor Isabel Hook. How is it to work with someone that was behind the original discovery? I mean,
Yeah, so,
do you feel like, I don't know, it's quite a privilege? Or do you just not think about
absolutely,
it?
yeah. So, I mean, I first met Isabel when I was an undergrad student. So she was a lecturer of mine in my 4th year. And at that time, I had no idea she worked on this dark energy project. So when I found that out, it was kind of, you know, well, I'm working with a science celebrity sort of moment. But I think she's really modest about it. She's a really great scientist, so she's teaching me a lot of stuff, and yeah, it's pretty amazing actually.
It's really good. And so before we move on and discuss a little bit more dark matter, I think we have an appropriate question from all the I don't know, incredible amount of people watching us now. So the voice from beyond, can you tell us the question?
Yes, Jean Collau asks, does the term dark matter refer to a specific kind of exotic matter that we may or may not know, or is it any object mass that we are unable to see in the electromagnetic spectrum?
I would say that's a pretty good question that maybe we can address. Karolina may give us some more insight, but it is possible that maybe dark matter is a mix of a lot of stuff.
Yeah, so I think the general consensus in the science community is that dark matter would be some type of exotic particle that we haven't discovered yet. And there are many proposals such as weakly interacting massive particles, supersymmetric particles, style neutrinos, all sorts of things. But then I do remember learning about this during my 2nd or 3rd year, I can't remember now. But there's a lot of speculation about that. You know, people have previously proposed brown dwarfs as candidates for dark matter, which are basically stars so dim that we could not detect them with our telescopes. And as David just mentioned before I started speaking, it is very much a possibility that dark matter could be made up of a mix of those things, you know? It doesn't have to be just one type of particle or one type of object which constitutes dark matter.
And Karolina, I guess if, I don't know, in the hypothesis that dark matter may be made of different things, could neutrinos play a role? Are there like good candidates for that to happen or not really?
So at first, it might seem like neutrinos are the ideal candidate for dark matter because they only interact via the weak force, which means they're weakly interacting, which would sort of fit the things we believe about dark matter. As well as this, from cosmological constraints on the upper mass limit of all of the neutrino species combined, and information from things like Big Bang nucleosynthesis, we can estimate how many neutrinos there are in the universe. And as it actually turns out, all of the neutrinos combined could have the same mass as all of the stars combined. So it might seem like a lot, but as it actually turns out, their combined gravitational effect would just not be large enough for this. As well as this, neutrinos are not a good dark matter candidate because they are very nearly massless. This means they propagate at relativistic speeds, which means that if they were to make up the dark matter, it would have to be the so-called hot dark matter. And again, I believe the general consensus in cosmology today is that hot dark matter is not a good candidate for dark matter, because if it was to move at relativistic speeds, it would prevent formation of small scale structures such as stars or galaxies. So unfortunately, the neutrinos we know of from the standard model are not the right place to look.
Or at least, I guess, not yet. So
Yeah.
but one thing that maybe some people are working on are like these, are there exotic neutrinos? I mean, we always evoke exotic stuff to explain.
Yeah, so another possibility would be this type of neutrino called the sterile neutrino. It gets its name from the fact that in contrast to the usual neutrinos we know of from the standard model, it does not interact via the weak force, which makes it even harder to detect than the usual neutrinos. We think it exists because recent experiments have observed this thing called low energy excess of electron neutrinos, which basically refers to the fact that we observe more electron neutrinos at low energies than allowed by our current theories of neutrino oscillations. And as it turns out, the existence of this fourth type of neutrino called the sterile neutrino could explain this low energy excess that we have observed. If this sterile neutrino exists, if it has the right mass, if there are enough of them, and if it participates in neutrino oscillations with other flavors of neutrino, as we think it might do, then neutrinos would form cold or warm dark matter, depending on the properties of this sterile neutrino. Therefore, if we do really discover it, that changes things, that turns things around by 180 degrees. And then maybe we can start looking again at neutrinos as candidates for dark matter.
It's definitely a lot of ifs, I see. But,
it is, but
it's always like that. It's better to have ifs than have no idea at all.
Exactly.
So I guess it would be really transformational for particle physics. Would it mean that we have to scrape everything up, or is it just specific parts of it that we need to change?
Not really. So there are a few things which are problematic with the standard model of neutrino physics. For example, it predicts that neutrinos have no mass, and we have known now for a couple of decades that they do indeed have mass, although it's very, very tiny. So aside from the fact that the existence of sterile neutrinos could potentially shine light on the dark matter problem, they could also explain how the standard three flavors of neutrinos we know of generate their mass via this thing called the seesaw mechanism. I believe that would not mean we would have to scrape everything we know about particle physics and the universe totally. It would only require a small extension to the standard model. So I think the discovery of the sterile neutrino would be ideal, as it wouldn't require us to tweak things too much.
Okay, so just enough to be exciting, but not enough to have to rebuild everything from scratch.
Exactly.
That's exactly what you want in science. That's the ideal discovery. John, we've talked a little bit about temperature of dark matter, and this may be quite confusing, right? So if we can't see dark matter, how can we put like a thermometer and measure its temperature? What do we mean by temperature?
Yeah, so that's a good question. So I think this has been touched on already. When we talk about things like hot dark matter, it's not necessarily to do with the temperature itself. So hot dark matter refers to particles, particularly in the early universe, that have a mass and travel at relativistic speeds, so speeds close to the speed of light. And in the very early universe, their energy was determined by the universe's temperature. So that's back when light and matter all interacted together. So that's what we mean by hot dark matter.
Yes, I go. I was just showing some very early universe.
Yeah, so this is the cosmic microwave background radiation. It's quite a famous image, as I'm sure a a lot of people will recognize it. So this is showing how the temperature across the universe changed. So there's areas of hot and low temperature, although the variation itself is quite small. So the reason for this is because as the universe expanded, it cooled down. And this allowed protons and electrons to come together and form hydrogen atoms. And the energy was low enough that they wouldn't automatically ionize. And because of this, the light would stop interacting with them. It'd be much harder for the light to collide with these atoms. And as the universe expands, these photons can then just travel freely. So they travel just in a straight line, and that's what we see as this background radiation that permeates the whole universe, and you get this lovely background radiation image.
And does that tell us anything about the temperature of dark matter? The cosmic microwave background, does it tell us something about dark matter, or is it like you need to make a lot of ifs and a lot of assumptions?
Yeah, so I'm not sure about this one exactly. So I guess in the early universe, when we have this hot dark matter, that model doesn't really work very well, because as the universe expands and cools down, it requires the density to, you got the density perturbations that result in galaxies. And when you've got hot dark matter, which dominates the matter content of the universe, this doesn't allow the galaxies to form until the universe is expanded enough. So it sort of contrasts with observations we have in cosmology. And that's why hot dark matter is not necessarily the best candidate for dark matter. It could be part of dark matter, but it's definitely not the whole picture.
So we can't have hot dark matter, but I guess it could be warmish or cold or just
lukewarm.
Yeah, a little bit warm, but not too much. Otherwise, we wouldn't be here. And that would be a bad thing. Karolina, I think we also have a question from someone at home. A voice from beyond.
Yes, we have. So João asks, at which point do expansions become too much? How would you decide when to scrap the standard model and start the new?
This is a very good question, actually. So personally, I would never scrap the standard model, and I don't think it will ever get scrapped by anyone, because while there might be some inconsistencies between its predictions and what you observe, the standard model of particle physics makes some of the best theoretical predictions in physics. It has some of the best agreements between experiment and theory. So I think it's more that we are missing something, and there is some physics out there that we haven't discovered yet, or maybe we don't understand things as well as we could. So what we need to do is carry on doing research to find out which pieces are missing, and then we can add it to the standard model to make it more complete.
I mean, it is a really fundamental question about science of when do you cut everything and start from scratch? And I guess now and again that needs to happen, but I'm sure that as a particle physicist, you definitely don't want to do that, because it would require relearning everything. So there's some inertia against it. John, I guess it would be great if we could learn a little bit more about how the hell we've detected dark energy. What are these things that you've mentioned, which are supernova 1A, and how they're useful? So could you explain a bit more how we can use supernova 1A to measure distances?
Sure.
Are they rulers? I mean, like, do we go there, put a ruler, and then push it back?
Well, not literally. So we can describe them as standard candles, but they're actually standardizable. So we have to make corrections to things like how the light changes over time and changes to the color. So they show very similar characteristics. So this is what we need to do before we can actually use them to measure distances. And so from theory, we have a good idea that they all explode at the same mass. So the most accepted model is you've got a binary system, so two stars orbiting each other, and one is accreting mass onto the other. So it's getting much more massive. And as this happens, the temperature increases, and it gets to a limit where the fusion going on will just result in a thermonuclear explosion, and it'll just be a runaway explosion. And this is what we see as the Type 1a supernova. And so because it explodes at this same mass, the brightness should be very standard. So this standard is what we take as the peak of brightness. So the light curve will start to increase and then it'll peak. And this is what we use to standardize these light curves. So
and I mean, in supernova 1a, I guess, are really useful for those at home, not just to measure distances, but most of the iron in our blood, our capability to like actually get oxygen comes from them. So it's thermonuclear.
There's a lot of interesting chemical reactions going on in these explosions. Yeah.
So when the team that I mean, essentially your supervisor was part of, when they discovered dark energy, I guess they were looking at these supernova, right? And what did they find? I mean, what was the observable that made them conclude that the universe was expanding in an accelerated way?
Yeah, so when they, so they're plotting the brightness of these objects against redshift, which is essentially the distance away. So in cosmology, when you're looking at really high distances, you like to use redshift because as the universe is expanding, things are moving away. So you've essentially got a Doppler effect, like how you have with ambulance sirens. So the light is stretched due to the expansion and it's shifted towards the redder wavelengths. So this is just a way to use, a way to explain the distance of these objects. And it appeared that these supernovae were much further away than we expected. And this could only be explained by an accelerated expansion of the universe.
And I guess I'm sure that I know if you find things or supernova that appear fainter, I guess they appear fainter. That's why we conclude that they're further away. I'm sure there's a lot of skepticism in science, right? For example, Karolina would be, I don't know, not tempted to scrap the standard model. And I'm pretty sure that in the 1990s, a lot of people resisted this crazy idea that the universe was expanding at an accelerated rate. And in astronomy, there's a saying that if you have an amazing result, it's always dust. So was it dust this time, and why not?
So dust could play a part in the light we observe. So if light goes through dust, it might be absorbed slightly, so appear fainter, and it could also cause reddening. But we can actually make these corrections to the supernovae. So, and yeah, it did seem really controversial at the time, but right now it's still the very sort of accepted thing that this is actually what we observed.
Karolina, I guess this is a question that I'm sure no one can answer, but have you thought about, in the standard model, there's always a particle and an antiparticle.
Yeah.
So are people considering the fact that dark matter may also have anti-dark matter? And if not, why not?
I'm sure that possibility is considered, but that would obviously depend on the nature of dark matter. So, for example, all of the particles we know of from the standard model, except neutrinos, have an antiparticle. So then you can ask, well, why couldn't dark matter? But then, you know, we have this problem of the universe exists. It's composed of matter. Where did all the antimatter go? So we think that at the beginning, shortly after the Big Bang, there was more matter than antimatter. So when matter comes with antimatter, it annihilates and gets converted to energy. And because there was more matter than antimatter, what we actually see around us right now is everything that's left over. So then you could ask, well, if there is if anti-dark matter exists, then where is it? And I guess you can keep going in circles like that. But yeah, I guess the answer is it would depend on the nature of the particle.
I guess you could go crazy and say that dark matter did not have an antiparticle, and that's why it kept being so much while, I don't know, matter annihilate themselves.
It could also be its own antiparticle. So neutrinos, actually, we are still not sure whether neutrinos have antiparticles. If they do, then they would be called Dirac particles. But there's also the possibility that they are their own antiparticles, in which case they're called Majorana particles. And, you know, we can't rule out the possibility that dark matter particles could also be Majorana.
So, I mean, neutrinos are not, I guess, to many standards, they're not so exotic because I guess, I mean, they're hard to detect, but we can detect them. We know they're there. We know some properties. So why is it so hard to know all these properties? Why haven't we figured that out yet?
I think, well, that's due to the fact that neutrino is the only neutral particle of the standard model. You know, all of the other particles, such as electrons, muons, all the quarks, we can tell them apart really easily because if they are charged, then we know that their antiparticles will have equal but opposite charge. And with neutrinos, because they are neutral, that leaves us with no way to tell, you know, which one it is. And there are many clever experiments on the way which are attempting to answer that question, but that's just like very complex, sophisticated particle physics.
So being, I guess, being neutral in particle physics makes you very mysterious, and it's very hard to find out. Now, obviously, I mean, all these field is very open, right? We don't know what dark energy or dark matter is or are, but are there surveys or missions that hopefully will shed more light on them? And I'll start with John. Are there specific surveys or missions that maybe you're even working with that you're really excited about?
Yeah, that's right. So in particular, LSST, the legacy survey of space and time, will be conducted by the Vera Rubin Observatory. So it's our astronomer that we mentioned earlier, Vera Rubin. She's now got a whole observatory named after her, which is great. So this is a facility currently being built in Chile. And I think it'll really revolutionize astronomical sky surveys. For example, it's going to get about 20 terabytes of data just every single night. And to try and put that in a bit of perspective, you know, a standard computer hard drive might be 1 terabyte. So imagine 20 computers just full of data just from one night of observations. And over 10 years, that's going to accumulate so much potential science. There's going to be some really interesting discoveries in there. And in particular, the supernovae. So the supernovae type 1a potential, which we can do dark energy with, will be a sample of, we expect, at least an order of magnitude greater than any previous survey. So I think, you know, the future is really looking bright for surveys such as this one.
Are you afraid that Elon Musk, for example, might screw this up a little bit with all the Starlink satellites,
yeah,
like triggering?
I think everyone's a bit afraid of Elon Musk for a lot of reasons. But yeah, definitely in astronomy, like there's so many studies being done already about the potential effect these satellites are going to have, and they can really contaminate your observations. So we're having to make these new additional algorithms that will try and account for these streaks you get across from the satellites. And by doing that, we might end up getting rid of potential scientific discoveries. And, you know, even if we do manage to get that successfully running, the amount of time they'll lose observing the actual night sky because of these satellites will be reduced so much. So it's definitely a big worry for a lot of scientists.
And Karolina, one thing that I was going to ask you is, how important is it for you, for example, that people are finally naming observatories and missions after amazing women? I mean, is it something that matters to you, or not really?
I think that is extremely important because it is very important to highlight the amazing work done by women in science, and that hasn't been the case up until very recently, because obviously women were not allowed to even participate in research for a long time. I think it will have an effect of, encouraging young girls to go into subjects which are traditionally dominated by men. And, I think it'll just help raise awareness. Still to this day, I read stories where female academic staff are mistaken for graduate students or postdocs in their own departments. And while that might not be intentional, I think it shows that sexism is still present and it's somehow ingrained in our brains. It's changing now, times are different. I'm sure the future will be even better. But one thing I always wonder is how much more would we know about the world we live in, not even just physics, if women were able to participate in science alongside men from the beginning of scientific revolution, so yeah.
Yeah, I mean, it's incredible how, that does happen, and science has excluded so many people for a lot of reasons, but hopefully we are on a better track. And John, in terms of the telescopes and the Vera Rubin Observatory, I think it's Vera Rubin Observatory, right?
Yeah.
A telescope. So you'll be looking, I guess, for supernova 1A, so you can improve the constraints on dark energy and what it is. But exactly how are you going to do that? How challenging is it? And what kind of things will you actually be detecting?
Yeah, so that's a good question. So, well, we need to be sure that the objects we're looking at are actually type 1A supernovae. So there's a lot of different types of supernovae out there. Traditionally, you want to get a spectrum of the supernovae, which will tell you what chemicals are in there. So, for example, the presence of silicon will tell you it's a type 1A supernova. And unfortunately, there's going to be so much data from LSST, which is good, but we're not going to be able to get spectra for all of these objects. So we need to have methods to just classify these supernovae based on the light we can see. So based on the light curve, so it explodes, it goes to a peak, and then it declines. We want to be able to use that and just that information to be able to give us the information we need to classify them. On top of that, we also need a redshift, which will tell us how far away they are. So for this case, you do need to get a spectrum, ideally. These are the most reliable ways to measure distance. So we don't necessarily need the spectrum of the supernova. We just need the spectrum of the host galaxy, which will make things a bit easier. So once we've got all this information, then we can do measurements for dark energy and constrain the parameters.
And I guess for normal supernova, there's a lot of neutrinos coming out. So Karolina, do you expect that at least in the future, neutrino astrophysics is actually going to be like a thing that it will be standard to do? And
yeah, I really do think that's going to be the case. Neutrinos are extremely hard to detect, and the era of astrophysics, neutrino physics kind of thing is only beginning. Now we are working on early supernova warnings, in which we basically warn astronomers when we expect a supernova to explode, and that's because we can actually observe the neutrinos coming from a supernova sometimes hours before we see the first light. I think the problem with supernova 1A is that there is not a significant amount of neutrinos escaping them, and with the neutrinos being so hard to detect, at the moment, it would be impossible for us to warn astronomers about type 1A supernova exploding. However, the science goes on, the detector physics advances every day. So hopefully in the upcoming years, we'll have good enough detectors to be able to, kick off the era of neutrino astronomy properly.
I mean, I guess in an ideal world, you can even use the fact that it's weak in neutrinos to distinguish between a more normal supernova and 1A. But
yeah. I mean, that would be ideal, but
That was
dream
cool.
on.
Could I add something to that?
Yeah, of course.
Yeah, so I saw some interesting news article recently that was, it was to do with a particle physics experiment in Antarctica, and they were trying to detect neutrinos in the atmosphere, and they actually detected a huge influx of neutrinos that seemed to come from the Earth, which seems to suggest that there was so many of them that a lot of them had managed to go through the Earth since they're weakly interacting and then go in the detector. And I think their explanation was something like it must have been some astrophysical event like a supernova. So I think if there's a way to sort of standardize the way they measure this, I think, you know, it could be really exciting potential there.
I mean, I guess a few years ago, no one believed we would ever detect gravitational waves. And I mean, now it's just like every day. And
It's all the rage now, isn't it?
it's beautiful. Yeah, it's always beautiful. The sound of merging black holes with gravitational wave detectors. Now, an important question is, I guess for you, John, what if dark energy is not real? What if you, I don't know, we do the experiments and we show that we just had it completely wrong? Is this possible?
I'm sure it's possible. I mean, dark energy is such an outlandish idea anyway. Like, I don't think people would be so surprised, but I wouldn't be too disappointed because I think if we can conclude with some sort of certainty that dark energy doesn't exist, then we must have learnt something that's really changing our fundamental understanding of the universe. So whatever has given us that result should be quite exciting.
I guess that's good. So even if it's bad news, it will be good news for the future. And John, so specifically on the work you're doing for your PhD, could you explain very briefly what you're doing and why it'll be important in the perspective of shining light on dark energy?
Sure. So this relates back to what I mentioned just previously, how we need to classify supernova based on purely their light. Because with LSST, there's going to be so many supernovae, it's going to be impossible to get spectra for all of them. So my work is currently involved in trying to optimize algorithms that can classify these supernovae just based purely on their light. And if we can do this with really high success, then we should get so many supernovae that will get a much higher degree of precision than any previous measurement on dark energy. And I think doing that, we can really shed some light on its true nature, if it does exist at all, that is.
And I think from YouTube, we do have a really relevant question of what you're just saying, right?
Yes, we have. So you talked about supernova types. Could you explain in a simple way what classifies a supernova and one type or another?
Yep, that's a really good question. So actually, a lot of people sort of disagree with how we currently classify supernovae. A lot of the classifications seem a bit ambiguous. It's probably easiest to separate them into thermonuclear explosions and core collapse. So the type 1A, as we mentioned before, are thermonuclear. So they accrete mass and they get to a mass limit and just explode. And there's core collapse ones, which can't support the mass of the star and collapse, and that causes the explosion. And these are then split into other subcategories that all depend on the exact sort of mechanics going on in these explosions and also the chemicals you see in them. So I hope that clears that up.
And Karolina, so you're moving on to do a PhD, of course, in neutrinos, because I mean, your passion for neutrinos is very obvious. What would you, I mean, if you could pick, what would be the discovery that you do within what's open in the neutrino field? What would you like to discover?
I think I'm going to have to say sterile neutrinos. As part of my PhD, I will be analysing the low energy excess at microboon, which I'm super excited about. And I don't expect to discover anything during my PhD, but it would be really exciting to discover the sterile neutrino in the future because, as we've discussed before, it could shed light on how neutrinos generate mass, hopefully allow us to extend the standard model. They make perfect dark matter candidates. Also, they have been theorized to have the capability to, violate CP symmetry, which is necessary for the universe to exist. So I feel like there are so many things tied to the sterile neutrino, so many things, so many answers it could potentially provide, that I think that would be my number one pick.
And I guess at least a Nobel Prize, I would say, if not two, if you get to solve all those problems. And I think we do have another question, which is related on the symmetry between matter and antimatter, right?
Yes, we have. So why this asymmetry between matter and antimatter? Would it not be expectable for them to be in the same quantity?
Yes, so that is the thing. We would actually expect matter and antimatter to be created in equal quantities during the Big Bang. However, as I've mentioned before, matter would annihilate with antimatter, and if there were really equal amounts of them, then there would be nothing left. And the fact that we exist says something about the fact that there must have been an asymmetry between matter and antimatter, in the early ages of the universe. And at the moment, this is a big thing in particle physics. We try to search for interactions which do violate this symmetry called the CP symmetry. We've already discovered a little bit of it in the quark sector. However, unfortunately, we know that it's not quite enough to account for the amount of matter we see. So again, neutrinos are the perfect way to search for the CP violation. We actually think that neutrino oscillations could violate the symmetry. So this is a big focus in neutrino physics at the moment.
Sounds very, very promising. And I'm sure you're convincing people to give more money to neutrino physics.
Hopefully.
Very good arguments. Now, just before we have the final questions, I'd like to ask both of you, and Karolina, I know that technically you're more into neutrino territory, which is kind of particle, but it is astroparticle. So I'm going to ask you if you have a favorite astronomer or someone you technically look up to, either scientifically or because of what they did.
In terms of astronomers, my favorites were always women who did their research early on, such as Vera Rubin or Henrietta Leavitt, if I'm pronouncing their surname correctly. They did their work during times when women weren't really, allowed to, go to universities, etc. And they've sort of infiltrated this male-dominated field, just like I've infiltrated this astro science talk show with my neutrinos. And they carried out some amazing groundbreaking research, which still to this day forms the core of our knowledge of the universe and things within it. So yeah, I think they were really amazing people, and they didn't get discouraged by the science community at the time, and I hope I never get discouraged from doing science like they never did.
Yeah, and Henrietta Leavitt, I'm sure many people will not know, but she basically, she invented everything beyond our own galaxy, because, she was the first one to get the distance ladder, or a way to get a cosmic ruler beyond our galaxy, which of course then extended to supernova 1A. And John, do you have a favorite astronomer?
It's a really tough question, that. I mean, when I think of astronomers, I think of the big sort of turning points. So I'll probably go with someone like Hubble, because that was sort of the dawn of cosmology, I suppose, because his observations showed us that the universe appears to be expanding, which even proved Einstein wrong. I mean, everyone knows Einstein, his name is synonymous with being a genius, but he thought the universe was static and not expanding, and everything sort of changed after that. So Yeah, I'd probably go with Hubble. I mean, his legacy is so huge. You've got the Hubble Space Telescope, the Hubble Constant. You know, his name is just everywhere in cosmology.
Even though, I mean, he got his measurements really wrong by factors of a few.
He did, but you know, he set the ball rolling.
Yeah, but he got the concept right. That's true. So that counts for something. So my final question is more of an opinion for both of you. So in terms of dark energy and dark matter making basically 95% of the universe, and we know very little about them, which component do you think we will kind of discover and understand first? Is it going to be dark matter or dark energy? And in a few years, we can watch this back and see.
Yeah.
I was gonna say, can we wait a few years?
Yeah.
Oh, that's a tough one. I want to say dark energy, but only because I'm a lot more familiar with what's going on in the dark energy community rather than dark matter. So, yeah, it's a tough one.
Dark energy.
I would say the opposite. I want to say dark matter because I mean, I might be a bit biased, but I do think that dark matter will be an exotic particle, and there's so much research going into it at the moment in a world of particle physics. So I do think it will be dark matter first, also because I feel like there is so much we don't know about the nature of dark energy. You know, for example, will the universe continue, you know, accelerating its expansion forever? Will we come to a stop? You know, will there be a big crunch? Is dark energy like a fundamental property of space-time, or is it some sort of mysterious force we don't know about? You know, I just feel like we don't know enough about dark energy yet.
Yeah, to be honest, now you said that, I want to change my answer.
Wow, it's already recorded.
I mean, I feel like it's a lot easier to sort of, I say easier to sort of do things with dark matter because, you know, we could sort of infer it in our own galaxy and do particle physics experiments. But with dark energy, it's just, you know, it's the whole universe we're looking at. So it's a bit more hand wavy what we're actually dealing with, you know.
Yeah, it's much more, I guess, at the start of the field, right? Dark matter is a little bit, I guess, more mature. But I see that the race is on between, I guess, a more astrophysics-based looking up and a more particle-based and detectors trying to detect what dark matter may be. And I guess the future will tell for sure. So I think that'll be basically all for today. Thank you so much again, Karolina, John, and the voice from
Cheers.
that you finally got to meet. I hope we can all find a way, obviously, to see the invisible and share it with everyone. We'll see whether it's dark matter or dark energy first. It was obviously really brilliant to have you. So you're definitely not invisible, and I'm sure you'll keep shining. So let's have a big round of applause to you from our audience. So thanks to everyone who watched, participated, and asked questions. We will be back next week with the amazing Taylor Hutchinson and Rebecca Larson, which will join us from the US to talk about discovering super distant galaxies with the largest telescopes in the world for yet another
The Earth is Flat on Planet Pluto.
Until then, don't forget to subscribe, I think somewhere here, on our YouTube channel. If you do speak Portuguese, you can join us also on Saturday where we have guests from Brazil. It's going to be amazing. And also you can catch up and watch other episodes on YouTube channel. So until then, keep looking up and hopefully we'll shed more light on the invisible universe. See you next time.
Liftoff of mission 41D, the first flight of the orbiter Discovery, and the shuttle has cleared the tower. Welcome home, Columbia. Beautiful, beautiful.
So I have to take it up for hangar, Joe?
We're going to dust it off first.
3, 2, 1, 0, and